first speaker today is Muthu, and he asked me not to say anything else about him, so I won't.
Thank you for coming in so early for the talk. I looked at the participants, realized that we are from many different communities. And what I'm trying to communicate is how people in my community, that's algorithms research, think about some of the problems that may be of common interest. And the one exercise I'd like you to keep in mind is the following. You are all experts in your respective areas. And it's difficult being an expert in algorithms because every computer scientist thinks they do algorithms. Right? Every cooking person thinks they do algorithms as well because they know the recipes are algorithms. But we know that algorithms research is a particular style of doing algorithms. And as a result, over time, I've developed this question that says, imagine you're in a party and somebody comes up and says that they work in your area. You want to think of a single question to ask them that if they know the answer, you'll be sure that they are an expert in the area. Okay? And the question should be reasonable. It should not be something that only you and a few other colleagues know about. And it should not be a gossip question. It should be a technical question. It should be. So if you think about this exercise, it's very valuable. Okay? In algorithms, I know the answer to this question. Okay? If somebody tells me they work on algorithms, I ask them, how much time does it take to find the median of n elements? Okay? If they say n log n, they don't know algorithms. If they say n, they know the algorithms research. Okay? I'd like you to do the same exercise with machine learning, other areas, and it's a worthwhile exercise. Okay? So it tells us how we target our research. And talking about targeting research, I was, Joshua was very nice to invite us for dinner, and I was talking to people in astronomy, and they were talking about research, and one of them said, it's not earth-shattering. So I was thinking that if you're an astronomer, you don't want to do earth-shattering research. You may want to do something else, but not earth-shattering. Okay. So we all have our metrics, and I'm going to communicate how algorithms researchers like me think about these problems. And you heard already a lot of algorithms researchers talk. You heard Suresh talk, you heard Petro's talk, and several others. So this is not new, but let's see if we can have some fun. So I'm going to talk about an area called data streams, which in the last 10 years or 15 years has become quite accepted as an area of research. And again, I've seen many different communities work on it, and I want to tell you my take on this. I'll start with a very simple puzzle that many of you have seen before. It's an interview question in Microsoft Research, I was told, or Microsoft Engineering. Okay. It's a good puzzle to start out with, and it leads to nice research as well. Okay. So in the puzzle, we have two players, A and B, Alice and Bob. And there are numbers 1 through n, 1, 2, 3, up to n. And what Alice does is takes these numbers, permutes the numbers, and shows numbers one after another to Bob, and just leaves out one of the numbers. So in other words, shows n minus 1 numbers to Bob. Okay. And what Bob needs to do is to figure out what was the missing number. What was the number that Alice did not show Bob? Now, of course, if you play this in reality with n equals to 4 or n equals to 10, we know the numbers 1 through 10, and if we play the role of Bob and if Alice showed the numbers, 9 numbers, in which she left out one of the numbers, it's easy for us to remember the 9 numbers that we've been shown and figure out what was the number that was not shown. Okay. On the other hand, if you play the same game with n equals to a million, it'll be difficult for us to remember all but 1 million numbers. Okay. So the idea is that we want to solve this problem when we're not allowed to store n bits. Right? If you're allowed to store n bits, the problem is trivial. You'll declare an array of size a1 through an and set the bit to 1 whenever you see a number. And then at the end of having seen all the n minus 1 numbers, you'll just make a sweep through the array and figure out what was the missing number. Okay? So it is a simple problem to solve. If Bob has full memory of n elements. And we're going to make the problem interesting by saying that Bob is going to have a very small number of bits, something like 2 log n. Okay. So then the question is, how would we solve this problem? And there's not much drama here. This is, as I said, a fairly simple puzzle, and has been used in interviews before. And the solution in this particular case is very simple. All that Bob does is every time Alice reveals a number, Bob keeps a running sum of the numbers that he has seen so far. Okay? So at the end of having seen n minus 1 numbers, Bob has a number s of sum of all the numbers seen so far. And Bob knows what the first n numbers add up to. N times n plus 1 over 2. And then if you subtract the sum from this max sum possible, you get the missing number. Okay? And why the solution works is because the sum of n numbers is like n squared. We need only 2 log n bits to store the sum. You don't need n bits to store the sum, so you can solve the problem in 2 log n. Okay. So it's a simple puzzle, but you can use it to motivate the fact that first, there are many times in which you can solve problems by storing much less information than what's in the whole input. And there's one in the beginning. If you now look at versions of this puzzle in which Alice leaves out 2 elements and 3 elements and so on, you pretty soon get to nice research questions. But this puzzle tells us that there are instances where we can solve problems without storing all the input. And in fact, something logarithmic in the input size. So many of you may have seen this puzzle, but I want to start this talk with a different puzzle. The idea is to find a median in one word. Just to remind people what a median is, if you have n numbers, median is a number which is the middle rank. So if you sort the n numbers, the item which has n over 2th rank, floor ceiling, is the median. Okay. It's a halfway point in the sorted order. So the problem here is that Alice now, there's not a single player game, it's Alice, and Alice sees items arriving one after another on a string. And at any given point, Alice has to be able to tell you what is the median of the elements seen thus far. Now, of course, again, as in stream cases, if you're not allowed, if you're allowed a lot of memory, you'll store all the elements and be able to find the median every time anybody asks for it. We're going to be particularly severe. Okay, in a minute. Okay. We're going to actually assume that there is some unknown distribution from which these elements are drawn. Okay. And the distributions go 1 to n, and elements are being drawn one after another. And Alice sees elements being drawn and has to maintain the median. But we're going to be particularly severe and say that all that Alice can remember is log n bits. Okay. Cannot remember n bits, cannot remember j bits for j items. It's just going to be log n bits. Okay. In other words, she can basically remember, Alice can remember only one number. The numbers are in the range of 1 through n, and Alice can only remember one number, and how does Alice get an estimate for the median? Now, it's a good puzzle, okay. And why would we care about this? After all, there's been an argument that memory is cheap, and why do we even restrict ourselves to doing this? There are good reasons for restricting our memory. One is that in many applications, the data comes very fast, and while memory is cheap, fast memory is not cheap. Second is that if you can store a small amount of memory and solve problems, you can use it to save in communication when you make the problem pairwise. If you take a problem and put it in m machines and you want to communicate amongst them, if you can solve the problem with a small amount of space, the communication is proportional to space, and therefore you save as well. Okay. So there are many good reasons why you'll want to work with small space. Of course, you don't have to be this draconian for being allowed to just have one word. But it helps because in certain database applications, you want to estimate the median of a stream, but the stream consists of many group bys. Okay. You want to maintain a stream of all the request delay times for every country, and the number of countries is 180 countries, or number of zip codes. So there are group by operations, and within each group by, you might want to maintain its median, so it's worthwhile to make the memory usage as small as possible for this problem. Okay. So now, having said that, this problem is really a motivation for us to do theoretical construct of sort of studying these limitations, and I would encourage you to think about this problem. Okay. Because when this problem arose in a lunch conversation, I had a solution in mind. It doesn't fully solve the problem. Like in all cases, you don't almost always. In almost all cases where you allow a small amount of memory, you cannot solve the problem exactly. You have to approximate something, and there's a little bit of an art on figuring out the right approximations that you can get out of a situation. So of course, there is an art to getting a solution and an approximation here, but there's an even further art to giving a hint to solve a problem. You know, I'm part of a cult of people who solve puzzles. Yesterday I had dinner with Peter Winkler, who's one of the great puzzle solvers, and he comes to have dinner with me, and in his pocket he takes out a puzzle. So there's a lot of puzzle solvers there, and one of the important things we know in solving puzzles is that you have to give people time to solve puzzles, and at some point they're going to ask you for a hint, and it's an art to figure out how to give a hint which gets them some way, but not all the way. Okay? So in this particular case, the hint I worked out was that there's absolutely only one thing you can do. That's all you have to keep in mind. Okay. To solve this problem, if you think about it, there's absolutely only one thing you can do. And that's all we can work with. Okay. So that's a good hint, and I'll let you figure this out. I'm not going to give you the solution. Okay. So those two puzzles are meant to say that there are problems, sometimes exactly or sometimes approximately. You can solve them with small amount of memory. And now there's been a theory for 15 years of what we can do with small amount of memory. And I have the advantage of being able to look back and say, oh, well, having done all this theory, could we abstract some very basic tools that we can communicate to others? And if you had the tool in your bag, you could solve problems on your own. Okay. So this is one such tool. Okay. So the talk is going to be sort of in two parts. One, first part is this basic tool, which we know for quite some time. And the second part is about the new tools that we're generating now, which we hope will be percolating over time into other applications. Okay. So the first tool is a tool for solving the following problem. You're given an array 1 through n. It's a large array, and it's going to be virtual in the sense you don't actually materialize this whole array. And what you see are updates to the array, which means that either an incremented item or a decremented item. So this array is tracking the frequency of each element. If you insert an element, that can be considered as adding 1 to its frequency. And if you delete an element, it can be considered as subtracting 1 from the frequency. So fi is the number of times you've seen I so far. So every time you see a new instance of I, you add 1 to it, and every time you delete it, you have minus 1. So fi is the frequency of I. And so you have this large array in mind, and you're seeing one after another of inserts and deletes into this collection. And what you want to do is to answer a simple question at some point when a query arrives and says, well, what is fi? In other words, how many times have you seen element I? Okay. You have to answer the frequency question. Now, as I mentioned, if I can materialize the entire array and sort of declare an array of size n, then obviously every operation can be done in constant time. You can increment, decrement in constant time. And then when somebody asks for a query of what is f10, f100, you can go look up the 10th or 100th element at the random access, and in constant time you can answer the question. Okay. So we know that this is trivial to solve if you allow full memory. What we're going to do is to make sure that we solve the problem with very small memory, okay, not even log n. Okay. So think of n as 1,000,000 or 10 to the power 12, but we want to solve the problem using 1,000 bytes, something much smaller than even log n. So by the way, once we understand the solution, we'll see why this is the core problem behind basically of most algorithms that we can do in small space. So here's how the algorithm is going to work. It's basically a simple table. Each row here corresponds to a hash function, and there are going to be log 1 over delta hash functions. So the solution that we're going to come up with is going to be approximate, and it's also going to be with high probability. Okay, so there's some probability of failure. So delta governs the probability of failure. So the number of hash functions is determined by the amount of success and failure that you want. And each hash function takes the array 1 through n and maps it into cells 1 through 1, something like 1 over epsilon. And epsilon is going to be the approximation. So the hash functions take n and reduce the universe down to something proportional to the 1 over epsilon, which governs approximation, while the number of hash functions govern the failure of success or failure probability. And what we're going to do is every time you initially everything initialize to 0, and when you see an update to an element I, you take I and use a hash function, h1 of I. The first it hashes to some element bucket. We're going to add one to this count here. Do that for every one of the hash functions. So for once, for people who want to get an idea of a hash function, think of it as something like ax plus b mod p. So h of x is a hash function which maps x to ax plus b mod p, where a and b are carefully chosen, and p is a carefully chosen prime. Okay, so it's a simple algebraic function, and that has a property of sort of taking x and sort of taking each element one after another, and you can sort of spread it out over the buckets randomly. Because we're going to choose this function randomly, the random one. So each hash function therefore maps each element to some bucket here in one row. So you track all the increments here, increments and decrements on this bucket here. Same thing with the second hash function, third hash function, and so on. So every time you see an update to an item I, you apply the update to each of the rows, and each row it will get applied to one of the cells or one of the buckets. And then when somebody will ask us to say, well, you know what, you're tracking this, tell me what is F10 or F100 or Fi. Again, we can take I and use this hash function to figure out where it lands. It will land in one bucket in each one of the rows. Each one of these buckets has a count. We just return the minimum value of it. And that's going to be our approximation. Okay. So this is a simple data structure. It's a table of counts, and we increment, decrement counts, and pull out some counts and return the minimum value. Those are the operations we perform. Now, what can we say about this function, this data structure? The estimate that we return will always be at least the correct value of f, because we're looking at all the places where I fell hashed into because of the various hash functions, and we're returning the minimum value. So whatever was fi, you contributed to each of those counters. So all that we can have is other items that have contributed to the bucket, but that will not lower the value. We're going to assume that all fi is greater than or equal to 0. We don't have any negative values. So wherever I falls, we took the counter and returned the minimum value, so fi definitely contributed each one of the counters. Some other people contributed to it, but that will not decrease estimate. So the estimate is at least the correct value, and it's at most the correct value plus epsilon times, it's going to be the approximation part, sum of all the other frequencies. So you have a large array. There are some elements which are 1, 10, 100, and some million somewhere, perhaps. Your estimation of any particular item says that you will return a correct value, at least a correct value, but at most a correct value plus epsilon times sum of all the items. Okay. So it's not a good relative approximation, meaning if the item was small, you don't get a good relative approximation to it. But if the item was large, you'll get a pretty good approximation, because if it dominates the whole function, the whole array, you'll get a good approximation. Okay. And that's the kind of guarantee you can get. So the other thing to observe is that the space we use is only 1 over epsilon times log 1 over delta. So epsilon is approximation, say 1 in 1,000 or something, and the probability is excessive 1 in 100. So this is going to be something like 1,000 bytes or a few hundred bytes. Well, n can be arbitrarily large. So the data structure that we keep is even independent of n. So we're not likely to get great approximation. So that's what is reflected in the kind of approximation guarantee we give. So it's a very small space, and the update time is very quick, right? Every time you increment, you just have to go and increment each one of the counters. There are only like 3 or 4 counters or 10 counters, log 1 over delta. So update is very fast. Space is different than n. But what we do of this is that we get an approximation rather than exact numbers. This is called the count win sketch. I'm not going to show you the proof. The proof is basically elementary. I'll tell you a little bit more editorial comments about the data structure. You might want to see whether, again, I'm not going to go through this proof as well, but I want to tell you what the result says. What I told you about the data structure, which has some approximation, some update time and space. And this argument here would argue that you cannot do better than that. You cannot do better than 1 over epsilon space if you want to get this kind of approximation that we did. Okay. So we use space proportional to 1 over epsilon. And if you had to use at least 1 over epsilon space to get this kind of guarantees we get. Okay. The proof is through a very simple reduction to something in communication complexity. If people are interested, I'll talk to you offline about it. Now, what's interesting about this data structure is that I've given talks about this to statisticians, and almost always the first thing that statistician would think about is that I can solve this problem by sampling. Okay? Because 1 over epsilon sounds like 1 over epsilon squared or 1 over epsilon, and there are sampling bounds. We know a lot about the sampling techniques, and so we should be able to solve the problem by sampling. Okay? The one thing I'd like to point out is that this structure is doing something quite non-trivial. It looks very simple, proof is simple, but it is doing something non-trivial. Because imagine this case where we have some arbitrary million items inserted in the data structure. Okay? And in order to only keep a small amount of memory, you have 1,000 items. Okay? Maybe you want to keep 1,000 samples. And then, that's your data structure here. That's all the memory you have of what happened in the past. And then somebody removes everything except 4 items. At this moment, you don't know which 4 items are going to remain. You're going to keep some information about what you've seen so far, but somebody removes all but 4 items, and ultimately only those 4 items, but you have a lot of space, 1,000 bytes now, or 1,000 samples. If you want to get a good estimate, you want to get answering questions on this, figure out which elements are present, and so on, sampling would have a difficult time doing this. Because if you're taking any sample of 1,000 items here, you have no idea which ones are going to be removed. You have very small probability of retaining the 4 items which are going to be removed. Right? In fact, for all possible sequence of what's going to come next, your sampling is not going to work. So the idea is that sampling is very good when you're adding items, so you're deleting items. You really have to figure out how to maybe even resample, etc. But you're seeing items one after another. Your memory is only whatever you've kept here. You're not going to go back and resample them. So on the other hand, this count data structure, count mean data structure I mentioned is a completely linear data structure. Okay. So if I kept 1,000 bytes of this distribution here so far, and then if I just remove all the items and just subtract out everything, it's all totally linear. Finally, what I would have would be a counting structure for the 4 items that are left behind, and that would be perfect. But now, if you want to estimate the frequency of any item with 1 in 1,000 of accuracy, you will actually figure out which items are exactly present in the data set. In other words, you saw a large number of items, you have a small number of bytes, but after a whole bunch of items are removed, you're able to exactly retrieve the 4 items which are left behind, no matter which of the 4 remain. Okay. So that's because of the linearity of this data structure. Okay. So this is just to explain to you why I wouldn't immediately assume that the kind of bounds we're getting can be obtained by even sophisticated sampling techniques. So what can you do with this? This looks like I'm talking about a third puzzle, right? And I talked about the first 2 puzzles, and this data structure looks like a third puzzle. Okay. The good news for us is that it's actually not a puzzle. It's the primitive on which you can build most algorithms that we know in this area. So if any of the people are database people, you know that indexing query means that you can keep items in a B tree, and you can look up any particular item. And once you have that, you can do range queries. Then you can do R tree. You can do a whole bunch of data SQL queries based on the data structure. It's something similar analogy here. Once you've figured out how to keep a large array that is being incremented and decremented with a small space so that you can answer any particular item query, you can use it as a building blocks to build a large number of algorithms. So for example, you can suddenly write a small piece of code. You have a bunch of data going by, you maintain a small data structure, and then later you can look at the data structure, what is F1, what is F2, what is F3, and you can ask all the Fn queries. Now, many of them will give you bad approximations because many of them will be very small items, but the ones which are large will get good estimate, and you can use that later on. Okay. So, and that's one way to use it. Similarly, as I mentioned, this is a linear data structure, which means if I have a distribution F and if you have a distribution G, and I want to look at what are the differences, then I can keep my data structure, subtract the data structure, just subtract arithmetic, and the result will be a sketch of the difference of the two streams. And then I can ask questions like, in the difference, what is the first element with second element frequency and so on, and figure out the large items in the difference. So you can do things like, what's the difference of the data from yesterday to today? From one location to another location. You can do all of this by operating on this sketch data structure. Right? You can do more with it. You have this large array N, and you can do something like wavelet kind of hierarchical decomposition. You can build a sketch not for this array F1 through Fn alone, but for an array in which you take two non-overlapping elements next to each other and collapse them into a half-size array, then another half, and so on, so logarithmic level of arrays. Think of all these virtual arrays, and you can compute a sketch for all of them in parallel. There's a log n extra memory, log n extra storage and computation. But once you have it, you can actually do very quick binary search through this array. If somebody wants to find out what's the sum of these bunch of numbers here, in other words, you ask, suppose these are frequencies of items sold in various zip codes, you can ask, what was the total sales in zip code 1010 to 200, 10010 to 20010, you can do a range query on this. And that'll be all logarithmic operations. So all of this can be done very quickly if you do logarithmic level of hierarchical sketches. None of these will be considered research in my area. These are all simple application of the basic tool once you have it. Right? We know how to build hierarchical trees, we can create them. You can use it to compute things like what are some of squares of frequencies. You can in fact take two vectors and compute the inner product. Okay. Again, to appropriate approximation, but you can do that by just taking count and multiplying them out and doing the right estimator. Okay. So notice that all these operations will be proportional to sketch size, okay, not proportional to the original data size. In fact, there's a very nice recent result that says that you can do matrix multiplication with a compressed way, in the sense that even if the matrix of size n squared, you can do the computation in time proportional to the number of non-zeros plus the size of the matrix n times the size of the sketch. This is like 1 over epsilon log 1 over delta. So this is nearly linear the number of non-zero elements, plus n is the number of the dimensions of the matrix times the sketch size. So in this nearly linear in the number of non-zero elements, you can get a pretty good estimate for the product of the two matrices. Now, Muthukrishnan talked about some of the results of this genre. This is a good result that goes beyond a lot of results that we know. In a sense, it's even less than quadratic time. It doesn't look at, getting some time proportional to n squared with an approximation of this type, you can do it. This result managed to get it something less than n squared, proportional number of non-zeros. And they give you some Frobenius norm type of approximations. What you can do is you can basically replace much of the sketch computation by the sketch I told you, and get a result which will be much faster, which will be much small space. This result will use 1 over epsilon squared bound to get the kind of approximation we'll get as 1 over epsilon. There are some details, Frobenius norm, L1 norm, we can talk about various people, but I'm presenting this, not the details of the result, but as an example of saying that once you have this tool, you should be able to approach any other result in the paper and say, well, they've done some algorithmic work, can I replace the code with some of these techniques and get something better? And it's fairly easy and trivial to do this. So what do we know about this sketch? It's been used for finding heavy thinners, heavy differences, and many of you know this area of compressed sensing. And you can, using just the Countman sketch I told you, you can basically get nearly the best compressed sensing result right now. Okay. So you don't need to have the RIP property, you don't need to have all this embedding metric property. You can basically use the Countman sketch and reproduce much of the compressed sensing results in an algorithmic way. Which is pretty exciting if you think about it. Okay. In the last few years, people have used this for natural language processing, machine learning. There are people who use this for hash kernels. I don't know what they are, but they use them. I intend to find out what they are, though. There's a very cute application of this data section is something called password checking problem, which got covered in New York Times. So basically, the idea is that rather than forcing people to think very carefully about what passwords they want to use with all these rules and conditions, you have a more natural way of choosing password, except that you have a very quick way of checking that there are no collisions. Okay? And they use this Countman sketch to check that there are no collisions. Okay? There are people writing code for this. There are in fact hardware implementation of the data structure. There are systems that use this. And there's a wiki site where you can see more and more about this. In fact, recently Joe Hellerstein sent a link to a nice implementation of CM Sketch in Madlib. It's a nice open source sort of parallel data structure, parallel database work that Joe's been doing, and this is one of the data structures he worked on putting it in. It's very nice. But this will give you a way to track what's going on there. So the summary here is that I'm stating a claim. The claim is not only due to the data structure, it's due to 15 years of work. The claim is that we used to believe earlier that polynomial time was great. If you can store all the data and work in polynomial time, you're in a good place. Or even linear time was a good goal, was a great goal. And now what these data structures do is to try to see that you don't have to capture all the data, you don't have to store all the data, you don't have to communicate all the data. You can do something sublinear in each one of the categories and still do many of the analysis we care about. And now, a lot of people have gone to making this argument. And I've seen this excitement come from many different areas, not only from theoretical computer science, but from signal processing, from other areas. It's very cool. Okay. Now, this is let me make you one editorial comment. This is called a sketch data structure. There are many sketch data structures out there. Okay. Like random projections, not all sketch data structures are the same. Okay. Like hashing, not all hashing is the same. Okay. There are many different data structures that differ on space use, time for update, what kind of estimates they can provide. Okay. And the reason why I talked about this sketch data structure other than others is that almost every other data structure I know more or less relies on Johnson-Lindell-Strauss type of embedding. They use space 1 over epsilon squared to get epsilon approximation. And you need it for some problems, but what this data structure does is it it uses 1 over epsilon space to get epsilon approximations for many problems that we actually care about, which we can use as a building block. Now, what's interesting about it is that if you've done anything in practice, epsilon tends to be like 1 in 100 or 1 in 1,000. So 1 over epsilon of 1,000 we can work with. 1 over epsilon squared of 1,000,000, it's hard to work with for memory space. So it makes a big difference whether you use 1 over epsilon or 1 over epsilon squared. And this is the only data structure I know that actually uses 1 over epsilon space. So it avoids going through Johnson-Lindell-Strass type of embedding for L2. And so it just directly solves the problems we care about and gets 1 over epsilon space. So that's something to keep in mind. It's used at this moment in for analyzing IP traffic packets as they go through the links. It's used, as far as I know, in every DSL head in this country that AT&T has. And they very crucially use this fact that the sketch is additive. It's part of a similar system in Sprint called CMON, where they use it to parallelize. It's also quite useful in decreasing communication if you wanted to distribute a data analysis, like they do in MapReduce-based computations. And well, it's been sort of very useful in this case. Is one of the challenges of this area has been that there's a lot of database communities that worked on this problem. And in database community, we choose to have general-purpose query languages and systems rather than systems that solve specific problems. So these systems solve specific problems of analyzing IP traffic data. You wouldn't want to use it to analyze Walmart sales. Okay, that's not what it's meant for. You can't run a SQL query and join them very nicely. Okay. These data structures are all, these systems are all specialized systems. So is this. So from a database point of view, a good question would be, can we actually make these streaming techniques fairly general purpose enough to have general streaming systems? And well, there will be claims that people are able to build prototypes of the type of this nature. I'm not convinced that we've been able to successfully addressing many of the sort of fundamental technical systems problems of building general data stream systems. So as far as I can tell, these techniques have been useful for specific, careful analysis, but not for general purpose SQL query or whatever. 5 minutes or no? I have time? Oh, very good. I think it was Preston who said that you're in real trouble when the audience looks at the watch. But you're in trouble when the audience looks at the watch, but you're in real trouble when they take the watch and shake it like this. I was walking up this morning from where I parked. For a moment, I thought I'm going to be late by 10 minutes, and I thought, no, this is a bad start. People are going to shake the watch even before I begin. That'll be really bad. Now, in a way, I'm aware that I'm talking to people who do fairly sophisticated analysis. They use R code, MATLAB, Mathematica, and they do very complicated analysis. And to them, simple things like finding what is the head location, like what's the difference, what are the big values, and so, et cetera, doesn't sound like a most complicated problem. Okay. But my claim is that if you give me a machine learning problem that you care about, and if we really have to make it small space, if the problem really demands large amount of this kind of resource constraints. Most problems don't. Most times people build the models and then do classification online or prediction online, then you don't need a small space. You don't need kind of resource constraints. But if you ever give me a problem where these resource constraints are real, then chances are we're going to solve them using some of these techniques. Okay, that's the argument, and so I wouldn't argue that these are the tools that you need for every problem that you solve. But if you do hit the resource constraints of the type these problems address, then these are the right techniques to use. So in that spirit, what I want to do is talk about sort of next generation of tools. So the tool I talked about is nice, useful, widely applicable. But it's also from several years ago, and we have gone on to other areas. We're now trying to look at new models, new ways of data analysis. And I thought, well, some of the tools like Counterman Sketch may be more, maybe known to some people. I thought what I'll do is sort of present an example of a few of the techniques that we have in the last couple of years, which are not as well known and may be useful. Okay. So after talking this morning, I sort of realized that maybe I should talk a little bit more about MapReduce or parallelizable code. There are wonderful efforts in the machine learning community on sort of MapReduce libraries, open source libraries for a lot of machine learning analysis. I haven't looked at all this stuff yet. Okay, but if anybody's interested in talking about MapReduce versions of these algorithms, I'll be happy to talk to them because I coded a bunch of this stuff in MapReduce, and I can literally talk about challenges of making these things parallel. I want to tell you about 3 different models that we're working with. Okay? And again, in each of those cases, I'm going to tell you the very simple problems we want to solve. Once you solve them, the rest of the structure will come together. Okay? So I'm going to start with the first problem, which is about monitoring something in a distributed world. Okay? So imagine there are a bunch of sensors, and they're all trying to talk to some centralized server or centralized sensor, and you want to compute something over the set of all sensors. Okay? Now, this is a very large set of class of problems. Sensors could be small, big, there could be power restrictions, communication, so on. And many of you have probably heard a lot of stories of this type. And I'm not going to tease out what is real, what's not real here, but I'm going to be motivated by this kind of conversation to pose a simple abstract problem that we need to solve. Okay? And the abstract problem is the following. You have a bunch of distributed nodes. And at time t, each of them has seen a multi-set of items. So S2T is a set of or multi-set of items seen by the sensor 2 up until time t. Okay. You can imagine this being measuring, say, the number of the identity of zebras that are passing through the sensor's vision point. Okay. Number of people going through a security counter, so on. Okay. So this is a set of people that go past the security viewpoint. So that would be a good way to visualize this. So there are n sensors or n sites, and each of them sees a bunch of items one after another. And up until time t, you have this st of I, which tells you what the sensor has seen that far. And then there's some central site here that has to compute a function over union of all these items seen so far. You might want to figure out, you look at all the people coming in and out of this campus, and you want to figure out how many different people use this building in a given day. Okay. So you're trying to do some aggregate computation on this collection here at the center site. Of course, the center doesn't observe these people, so these sensors have to communicate to the center. Okay. Now, if we look at the number of bits being sent from this the site to the center, and what we want to do is to minimize. Excuse me. We will be focusing on the number of communication of the bits and trying to do it as small communication as possible. But to instantiate this study, I'm going to look at a simple problem that says that let S be the multi-set union of all items. Okay. Just to make the conversation easier, let's assume that each site sees a set of items, not a multi-set, okay, which means the same item doesn't appear more than once. And what we're trying to figure out is what is the size of the union. Okay. More precisely, we're saying that the center is going to say if the union size is more than some threshold tab, it's going to say, well, output 1, otherwise it's going to output 0. In other words, what the center is trying to figure out is count up to a threshold and say, if there are more than this many people in the union, then I want to say 1, otherwise I say 0. Okay. So it's simply detecting the threshold of the total union size. We're going to give us a little bit of room and say that the center will output a 1 if the total number of people is more than tau. It should output a 0 if the number of people is less than tau minus epsilon. And between epsilon, tau minus epsilon, and tau, we don't really care about the state of that. Because we're going to approximate an account, so we're going to give ourselves some room there. Okay. So that's the output we want. Now, a trivial way to do this is that every time any of the sensors sees a person or a new item, they send the identical person to the center. Okay. Or say plus 1 to the center. Then all the center has to keep the total sum, and as soon as it goes close to tau, it says 1, or exceeds tau, it will say 1. So, if any time anybody sees any new item, if the set is plus 1 to the center, then you'll be able to solve this problem exactly. But that will require a total number of bits proportional to the number of items seen so far. Okay. And what we want to do is solve the problem using fewer number of bits. In other words, we want to minimize the total sum of number of bits sent from each one of the sources to the center over the whole time. This sounds like a little bit of a made-up problem, but it's not. Now, what you're really trying to say is that assuming that there are n sensors and see different sets of people, and keep seeing people coming in, you're trying to figure out, tell me when the total number of people exceeds some number. Now, if I do that the one-shot computation, it's very easy, right? At any given moment, I call each sensor and tell me how many people I've seen, and I add up the sum. But that's not what we want to do. We want it to be continuously monitored, and as soon as the total number of people exceeds, that's when you want to ping. Now, if you're a programmer, the way you solve the problem is to say that every 5 minutes poll, so that you're accurate up to 5 minutes, 10 minutes. Okay. But that's not what we want to do here. We want to be accurate at this. Okay. We're not going to call periodically every 5 minutes to call each one of the sensors. We just want the sensors to work in a graceful way and let you know when the threshold is exceeded. Okay. So it's called a distributed continual monitoring problem. It's distributed because of a bunch of sensors. It's continual because you want the whole thing to work continuously. You don't want to every few minutes poll. You don't want it to stop and ask at the end of the day and so on. You just want it to output any time the threshold is exceeded. Okay. And our goal is to minimize the number of bits. Okay. Now, I don't have time to describe the full solution in the full proof, but I'll tell you the nature of the result I'm looking for. Okay. One result would be to send every time a new item arrives, send a bit to the center. That's a trivial solution. And no matter how you think about the problem, it feels like you cannot solve this problem without having every node send at least one bit. It looks like n should be some sort of a lower bound for solving this problem. And that's what we thought for quantum. In fact, that's a lower bound for deterministic algorithms. But if you think about a little bit, what you want to do is something like this, right? So assuming that you know, think of a solution with two sensors. Each sensor is going to say, no, I see a new item. Should I tell the center or not? Well, now if I know that I'm very far from the threshold, if the total sum is very far from the threshold tau, I don't have to tell the center immediately. I can wait for some time. I can in fact wait until I see like tau over 2 elements. Because if the other person is also doing the same algorithm, when they see tau over 2 elements, they will send an element ping to the center, and I can just wait. And that's already a good approximation of the tau answer. So you sort of realize that you don't have to send a bit every time you see a new element. You only have to send a bit every time some sort of thresholds are reached. Okay. And then you realize that you don't even have to send a bit every time the threshold is reached. You need to count sort of how many thresholds are reached, local thresholds reached, and you can do that by randomized counting. So roughly the algorithm would look like each one of them will have a threshold of tau over n, and they'll say that whenever I reach a multiple of tau over elements, I'll send with some probability, I'll send a bit to the center. And the probability will be like 1 over epsilon squared, that's a sampling kind of probability. And that will be sufficient to give you this approximation of tau minus epsilon in all these steps. Okay. So the main idea trying to communicate is that there are instances where you don't have to send every bit. There are in fact instances where you don't have to send every bit when you see like half of the items or 1/3 of the items and so on. You can choose to send bits with the randomization, with the randomized probability, and that would be enough to give you a right approximate guarantee of the center. Okay. So if we're able to solve this problem using something like 1 over epsilon square bits, which is pretty amazing, given the number of sensors that you want to look at as n as a parameter. So I don't have time to go through the proof. The way, but I do want to connect. Once you set up this basic algorithm, we're able to use similar algorithms to keep track of, in fact, how many different distinct people go through the network, how to cluster the endpoints. Each of the sensors sees a bunch of points, and they want to keep making a clustering of all union of the points. We can still do that with sublinear communication. So we can do a compressed sensing problem in this model right now. Okay. Assuming that each sensor is seeing a signal and the signal keeps changing, we can, in the center, keep a small dictionary representation of the union of all the signals. Okay, which is pretty nice as well. Okay. So we can solve all of these problems right now with reasonable approximation using this idea of figuring out when to send the randomized signals. And the connection I would draw would be that there's a beautiful selective Wolf theorem that says that two sources can communicate even when they don't synchronize with each other at a rate that is related to the sort of mutual information. It's a very beautiful theory. We are doing something, you have to sort of keep that roughly in mind. We're trying to develop that in a discrete way over a bunch of sources. Okay. If people are interested, I can have a conversation about it. Okay. Now, this is only the beginning of a theory. You don't need to have sensors talk to a center. You can have sensors talk to the intermediate nodes, and you can have a tree structure, you can have a DAG structure, and you can try to extend all this theory to all these structures. But what I wanted to tell you was just a simple problem which you might be able to think of when you take a lunch break, and already give you basics of how we start thinking about other structures. I'm going to talk through two other examples. There are two other sets of models, other models we work on which are interesting in general to the science community. One is a model in which we see a sequence of items, and each item is a probability function. Why would this be interesting? You can imagine seeing a sequence of web searches, and each of them being tagged by a machine learning algorithm as being some distribution of whether it's spam or not a spam, or whether it's a click or not a click, and so on. So you can imagine a sequence of items, each one of which is a small probability distribution function, and you want to talk about the sort of space of all sequences you can generate using the sequence of probability distribution functions. We can reason about such things, again, in small amount of space. There's another model called stochastic model which I really like, which is of the following type. You know that the items are going to be drawn from some distribution, and you can even compute some statistics for the distribution. But the problem we have is that we are seeing n items drawn from the distribution, and you must compute a statistics on the empirical values that you see here. So it's not that you compute a value from the distribution and then declare that as an answer. That answer has to be correct for the particular empirical distribution you see. Now, there's not much difference between these two views if you look at simple statistics like averages, etc. But if I said I want to find a median of n elements, and you find a median of the distribution, that's not necessarily the median of the empirical distribution that you see. So we want an answer which is good for every draw of sequence of draws that you see. It's called stochastic streaming problems. We have ways of addressing some of these problems as well. The theory is not as well developed, but this is a good model to think about. Just quite recently, we've been able to develop techniques for being able to take a large graph and come up with a small sketch so that you can follow the edges of the graph. I didn't want to mention it because I didn't think graphs by themselves are interesting in this community, but the tools behind it may be interesting to the community. That's something to keep in mind. Now, in each of these cases, what we have done is we sort of sketched this plausible mathematical world and the mathematical problem. The mathematical techniques are interesting, and they give us new ways to think about the problem. But unfortunately, we don't really have many compelling systems. We don't have any compelling applications, therefore we don't have good systems to build around it. Okay. I've now actually seen a sensor network where I need to continuously track this the statistical value. Right? So we're sort of struggling with trying to find good applications where this theory can be applied or can be motivated. So I thought I'll have it up here because some of you may have examples of where this matters. For stochastic streams, I did find a good motivation for it in Google Google advertising. Even if you know the distribution of what's going to happen the following day, the particular draw that you see that's going to happen on a given day is going to be different, and we want to be good with respect to the particular draw. And so this has led to some very nice research on online ad allocation problems. Okay, so I think there's a good reasonable model there. The probabilistic data model is very popular in the database community, and there's reasonable attempts at prototypes of somewhat probabilistic data query processing engines. But again, from my point of view, I'm looking for compelling applications, so I should build out such systems. Now, for me, the research happens when you not only solve puzzles and have theorems, but you also find the right application where you can build a system and help you motivate your research. In the basic data streams, we had such an application in analyzing IP traffic data. We haven't found such application for some of the other models I mentioned. I left out things like analyzing not the entire stream, but a window of stream. There are many models of window stream. So you don't want to, if you're looking at a series of data, you may not want to analyze all the data seen thus far, but you may want to analyze the last 1 hour, or trading 1 hour, etc. Those are window streams. There are a lot of women of work on doing much richer queries, and they talk about things like clustering problems. Again, in appropriate models, we can solve clustering models using the government sketch I talked about. So you have a good handle for approaching the problem. In fact, if you want to do, I don't know, support virtual machines, if you want to do some sort of approximation to the slope, and if you have space constraint, then you can use this technique to get good approximations there as well. I haven't talked about things like how to analyze map-reduced computations I mentioned. I'm happy to talk to people offline. There is a very nice connection between this kind of analysis and privacy. For the people who are following the developments, there's been a very nice model called differential privacy for the last 10 years that gives you a way to reason mathematically about privacy of data analysis. And there's a variation of that model called pan-privacy, which I really like. Initially, the motivation came from saying that assuming you're doing computation privately and you claim that it's private, it's great, but if somebody breaks in and looks at your program or the state of the code, then you end up compromising many things. Like, a good example, think about, imagine that you're keeping track of your employees and the salaries, and if someone asks for average salary or a good differential private solution is to take the salaries, compute the average, add some noise, and return that as an answer. The differential privacy theory will tell you that that's a good answer. But now if you maintain the solution, if somebody breaks and looks at a data structure, then they know everybody's salaries. Okay. So you can be private but not secure. Okay. What pan-privacy does is to develop a model that says I want to address security and privacy together. I want a computation which is, even if somebody breaks in, you will not reveal any information about the users, and the output will be differentially private. It's a great goal, and they formulated a very clean model. And what I'm able to do now is reproduce many of the streaming results in the span-private model. And there's a beautiful philosophical question here, which is, the span-private model by itself doesn't require you to work with any small space. You can take the input, you can have quadratic space, cubic space, and you can do the computation as long as your differential private is secure. And it turns out that our lower bounds are against such arbitrary computations, but upper bounds all use streaming algorithms. In other words, they use a very small amount of memory. So it's sort of philosophically interesting that if you want to guarantee security of your private data, you simply want to use as small bits as possible in the storage. And so we're working through details of that. That is actually the end of my talk. So thank you very much.
Questions?
Thanks, Muthu. That was really interesting. I'm kind of curious about the epsilon versus epsilon squared distinction. It seems like the epsilon squared results kind of come in when we want to measure distances with respect to two norms or convenience norms or things like that. And it sort of seems like here we're doing things with respect to like one norm, something like your matrix product result. Could you maybe sort of talk about the geometry there? Does that matter?
It's a great question. I've struggled with this for quite some time. When I saw the sketches for the first time, they used 1 over epsilon square space. And because they were being used for estimating the L2 norm, and so they involve Johnson-Lindenstrass embedding, and you can show a lower bound of 1 over epsilon square. And then I asked sure, you need this for estimating this L2 distance, but do you need it for anything else? Okay. And turns out for anything like joint sizes, finding big differences, for signal processing, you don't need L2 estimation at all. So you don't need distance preserving L2 embeddings for answering questions like what's the best k-term representation for a signal, for the best k clustering. Okay, and it's just that for a long time the community went down the path of using 1 over epsilon square space because they had the other handle, the Johnson-Lindenstrass based sketch of 1 over epsilon square size, and they used it as a handle to solve all these problems. But what this line of research says is that at least for solving these problems that we care about, you don't need this L2 embedding. Of course, if you now want to use it for L2 estimation, then you have to increase the sketch size to 1 over epsilon square. And you can do the same thing, you can do that with the same data structure. You just increase the width and take some alternate differences. You know, +1, -1 embedding, you can do that. Essentially the same sketch will give you, but you need more width and more space. In fact, technically, this will end up improving Alon Mathias's kind of main results because it'll increase its width to 1 over epsilon square, but the update time will be log 1 over delta. So it'll be faster in update than the normal sketches. But that's, you need to do it only if you want to do distance preservation. Okay. And you're right that there are applications where you need distance preservation, maybe nearest neighbors kind of computations. But part of the fun has been sort of getting around it using L1. So the matrix result I mentioned, they found out was specifically put there to say that much of the hard work you need using more space, etc. Now, at least you can do as an exercise. You can replace it with L1 and see what you get. Sometimes you don't get a good result, I'll be honest, and sometimes you get lucky.
So as a follow-up on that, I was just curious that if you get the approximation guarantee though in terms of the L1 norm of the data stream, that seems like it could be potentially much larger than an approximation guarantee in terms of the L2 norm, which distance preserving embedding might give you though, right? So is that seen when you apply these systems in some of the applications you mentioned, or how does that compare?
So, there is this, you can do the following. You can take a particular point theory estimate, Fi, and say, can I get an L1 estimate for this using one over epsilon space? And can I get an L2 guarantee in error using one over epsilon space and compare the accuracy versus the space used? And in some cases, like the initial problem I mentioned, you'll be actually able to show that L1 guarantee is not that good. In other problems, surprisingly, no, first of all, theoretically, you'll be able to show that they're incompatible. You won't be able to beat because L2, depending on how the vectors are structured, either uniform or biased, you won't be able to, you'll be incomparable. And then you have to use experiments to compare. So for example, Theodore and his student did computations with this for compressed sensing. And they found the confidence sketch was doing well. In fact, the best curve is confidence sketch in that case. Even though you'll find an L2 and L1 guarantee incomparable. Roughly, the guarantee will be L1 over epsilon, L2 over square root of sketch size, and those are the two things that you compare. And in many applications, they're incomparable. Some applications, L1 is worse than L2, and then you have to result in experiments in the bush case.
So I would just add a comment that I think a number of people here have already started asking questions about searching on graphs and best searching on graphs. So I think there's going to be broad applicability, maybe not so much in some types of physical sciences, but there's certainly for information querying, graphs are becoming very important. So I certainly encourage you to talk about that for the time that you're here. I wanted to ask the audience if anyone who didn't know the answer to the median question before coming to the room today knows the answer. You get a free lunch. Okay, we'll have to talk about that offline. Well, let's thank our speaker again. Thanks for a great talk.
You may want to do something else, but not in general. So we all have our metrics, and I'm going to communicate how algorithms researchers like me think about these problems. And you heard already a lot of algorithms researchers talk. You heard Suresh talk, you heard Petro's talk, and several others. So this is not new, but let's see if we can have some fun. So I'm going to talk about an area called data streams, which in the last 10 years or 15 years has become quite accepted as an area of research. And again, many different communities work on it, and I want to tell you my take on this. I'll start with a very simple puzzle that many of you have seen before. It's an interview question in Microsoft Research, I was told, or Microsoft Engineering. Okay. It's a good puzzle to start out with, and it leads to nice research as well. Okay. So in the puzzle, we have two players, A and B, Alice and Bob, and there are numbers 1 through n, 1, 2, 3 up to n. And what Alice does is takes these numbers, permutes the numbers, and shows numbers one after another to Bob, and just leaves out one of the numbers. So in other words, shows n minus 1 numbers to Bob. Okay. And what Bob needs to do is to figure out what was the missing number. What was the number that Alice did not show Bob? Now, of course, if you play this in reality with n equals to 4 or n equals to 10, we know the numbers 1 through 10, and if we play the role of Bob, and if Alice showed the numbers, 9 numbers, in which she left out one of the numbers, it's easy for us to remember the 9 numbers that we've been shown and figure out what was the number that was not shown. Okay. On the other hand, if you play the same game with n equals to a million, it'll be difficult for us to remember all but 1 million numbers. Okay. So the idea is that we want to solve this problem when we are not allowed to store n bits. Right? If you're allowed to store n bits, the problem is trivial. You'll declare an array of size a1 through an and set the bit to 1 whenever you see a number, and then at the end of having seen all the n minus 1 numbers, you'll just make a sweep through the array and figure out what was the missing number. Okay? So it is a simple problem to solve. If Bob has full memory of n elements, and we're going to make the problem interesting by saying that Bob is going to have a very small number of bits, something like 2 log n. So then the question is, how would you solve this problem? And there's not much drama here. This is, as I said, a fairly simple puzzle, and has been used in interviews before. And the solution in this particular case is very simple. All that Bob does is every time Alice reveals a number, Bob keeps a running sum of the numbers that he's seen so far. Okay? So at the end of having seen n minus 1 numbers, Bob has a number s of sum of all the numbers seen so far, and Bob knows what the first n numbers add up to, n times n plus 1 over 2. And then if you subtract the sum from this max sum possible, you get the missing number. Okay? And why the solution works is because the sum of n numbers is like n squared. We need only 2 log n bits to store the sum. You don't need n bits to store the sum, so you can solve the problem with 2 log n bits. Okay. So it's a simple puzzle, but you can use it to motivate the fact that first, there are many times in which you can solve problems by storing much less information than what's in the whole input. And there's one at the beginning. If you now look at versions of this puzzle in which Alice leaves out 2 elements, 3 elements, and so on, you pretty soon get to nice research questions. But this puzzle tells us that there are instances where we can solve problems without storing all the input. And in fact, something logarithmic in the input side. So many of you may have seen this puzzle, but I want to start this talk with a different puzzle. The idea is to find a median in one word. Just to remind people what a median is, if you have n numbers, median is a number which is the middle rank. So if you sort the n numbers, the item which has n over 2th rank, floor ceiling, is the median. Okay. It's a halfway point in the sorted order. So the problem here is that Alice now, there's only a single player game, it's Alice, and Alice sees items arriving one after another on a string. And at any given point, Alice has to be able to tell you what is the median of the elements seen thus far. Now, of course, as I said again, as in stream cases, if you're not allowed, if you're allowed a lot of memory, you'll store all the elements and be able to find the median every time anybody asks for it. We're going to be particularly severe. Okay, in a minute. Okay. We're going to actually assume that there is some unknown distribution from which these elements are drawn. Okay. And the distributions over 1 to n, and elements are being drawn one after another. And Alice sees elements being drawn and has to maintain the median. But we're going to be particularly severe and say that all that Alice can remember is log n bits. Okay. Cannot remember n bits, cannot remember j bits for j items. It's just going to be log n bits. Okay. In other words, you can basically remember, Alice can remember only one number. The numbers are in the range of 1 through n, and Alice can only remember one number, and how does Alice get an estimate for the median? Okay. Now, it's a good puzzle. Okay. And why would we care about this? After all, there's been argument that memory is cheap, and why do we even restrict ourselves to doing this? There are good reasons for restricting our memory. One is that in many applications, the data comes very fast, and while memory is cheap, fast memory is not cheap. Second is that if you can store small amount of memory and solve problems, you can use it to save in communication when you make the problem parallelized. If you take a problem and put it into m machines and you want to communicate amongst them, if you can solve the problem with a small amount of space, the communication is proportional to space, and therefore you save as well. Okay. So there are many good reasons why you'll want to work with small space. Of course, you don't have to be this draconian for being allowed to just have one work. But it helps because in certain database applications, you want to estimate the median of a stream, but the stream consists of many group bys. Okay. You want to maintain a stream of all the request delay times for every country, and the number of countries is 180 countries, or number of zip codes. So there are group by operations, and within each group by, you might want to maintain its median, so it's worthwhile to make the memory usage as small as possible for this problem. Okay. So now, having said that, this problem is really a motivation for us to do theoretical construct of sort of studying these limitations, and I would encourage you to think about this problem. Okay. Because when this problem arose in a lunch conversation, I had a solution in mind. It doesn't fully solve the problem. Like in all cases, you don't almost always. In almost all cases where you allow a small amount of memory, you cannot solve the problem exactly. You have to approximate something. And there's a little bit of an art on figuring out the right approximations that you can get out of a situation. So of course, there is an art to getting a solution and an approximation here, but there is an even further art to giving a hint to solve a problem. I'm part of a cult of people who solve puzzles. I yesterday had dinner with Peter Winkler, who's one of the great puzzle solvers, and he comes to have dinner with me, and in his pocket he takes out a puzzle. So there's a lot of puzzle solvers there, and one of the important things we know in solving puzzles is that you have to give people time to solve puzzles, and at some point they're going to ask you for a hint, and it's an art to figure out how to give a hint which gets them some way, but not all the way. Okay? So in this particular case, the hint I worked out was that there's absolutely only one thing you can do. That's all you have to keep in mind. Okay? To solve this problem, if you think about it, there's absolutely only one thing you can do, and that's all we can work with. Okay? So that's a good hint, and I'll let you figure this out. I'm not going to give you the solution. So those two puzzles are meant to say that there are problems, sometimes exactly or sometimes approximately. You can solve them with small amount of memory. And now there's been a theory for 15 years of what we...
Our first speaker today is Muthu, and he asked me not to say anything else about him, so I'm not.
Thank you for coming in so early for the talk. I looked at the participants, realized that we are from many different communities. And what I'm trying to communicate is how people in my community, that's algorithms research, think about some of the problems that may be of common interest. And the one exercise I'd like you to keep in mind is the following. You are all experts in your respective areas. And it's difficult being an expert in algorithms because every computer scientist thinks they do algorithms. Right? Every cooking person thinks they do algorithms as well because they know the recipes are algorithms. But we know that algorithms research is a particular style of doing algorithms. And as a result, over time, I've developed this question that says, imagine you're in a party and somebody comes up and says that they work in your area. You want to think of a single question to ask them that if they know the answer, you'll be sure that they're an expert in the area. Okay? And the question should be reasonable. It should not be something that only you and a few other colleagues know about. And it should not be a gossip question, it should be a technical question. It should be, so if you think about this exercise, it's very valuable. Okay? In algorithms, I know the answer to this question. Okay? If somebody tells me they work on algorithms, I ask them, how much time does it take to find the median of n elements? Okay? If they say n log n, they don't know algorithms. If they say n, they know the algorithms research. Okay? I'd like you to do the same exercise with machine learning, other areas, and it's a worthwhile exercise. Okay? So it tells us how we target our research. And talking about targeting research, I was, Joshua was very nice to invite us for dinner, and I was talking to people in astronomy, and they were talking about research, and one of them said, it's not earth-shattering. So I was thinking that if you're an astronomer, you don't want to do earth-shattering research.